electronics. So what is a roofline model? Roofline model is a simple, mathematical abstraction. Okay. Here the whole idea is to do bound and bottleneck analysis. Okay. That means what is the upper bound of the performance for a particular system. That means see, suppose I purchase this machine or my laptop. I don't know which application I will run, but at least I should be able to find out, what is the maximum performance I can get from this system. That is the idea of roofline model. Okay, so that is the so now in any program we do two things. One is we do memory access, right? Get the data and do the computation. Okay, I hope this is very simple. Get the data, do the computation. Now each of them takes some time, so the time consumed by the program is the higher of the two. Okay, I hope this is very simple, right? If you're doing two things, whichever takes more time, that decides your total time. So this intuition is captured by the roofline model.
Sir, not the addition of the two times. Why higher of the two?
We are doing in parallel. We are not doing one. We are not doing sequentially. We are doing one in parallel. Okay. So this is the definition of the roofline model. So the maximum performance you can get from a system. So remember, roofline model is defined for a system. Okay. And arithmetic is arithmetic intensity that is defined for a particular application. This is a very crucial difference. Don't get confused. Roofline model is for a particular hardware. Suppose you have a laptop, GPU, CPU, FPGA, ASIC, whatever you have. Roofline model is defined for that hardware or for that system. And arithmetic intensity refers to a particular applications or particular program that you have. For that, you use the arithmetic intensity. Okay. So now, so here AI is the, so remember one more thing is AI here is not artificial intelligence. AI is arithmetic intensity. Okay. AI is arithmetic intensity. So, the attainable performance on a particular system is the minimum of your maximum computation performance, this one, and AI, which is your applications. AI is arithmetic intensity multiplied by the memory bandwidth. So here you assume you are just bypassing the cache. So forget cache. That means whenever you're doing computation, you're directly getting the data from the main memory. This is like a worst case, right? So that means the memory bandwidth. So AI is what? We will define AI very soon. But whatever is the arithmetic intensity for now, you just assume we have some certain arithmetic intensity multiplied by the bandwidth. So whichever of the two values is lower, that is the maximum performance you can get. Your actual performance can be even lower. It cannot be higher than that. Okay. So now you can see we have captured machine value. So flop per second depends on the system, right? I will give examples. And bandwidth also depends on your system. That means whatever memory you have. If you have GDDR, DDR, HBM, whichever memory you have, that bandwidth will decide the bandwidth value. And AI is for the program. Okay, so as you can see, of course, performance will depend both on the replication and the system. That's what we have captured here. Okay. Now, what is arithmetic intensity? Let us define that. So this is for the application, right? This is the metric for the application. So what arithmetic intensity is? For each byte of data that we fetch from the DRAM, how much number of floating point operations we do on that byte? Okay. So now I hope everybody knows. Suppose we have a n cross n matrix. Okay. Suppose we multiply two matrices. So we fetch one n into n matrix and another n into n matrix, right? So total we have fetched two n into n. And now if you know like complexity analysis little bit, we always ignore this part. So the complexity of, I mean, how much data we are fetching is order of n square. Right? I hope everybody at least knows a little bit about it. Even if you don't know the full complexity theory, but at least you know that this too, we can avoid all this because we just want to see how it scales. And how many operations are there in the matrix multiplication if we are multiplying two n by n matrices? Anybody knows how many matrix multiplication of, I mean, how many operations we do in a matrix multiplication computation?
N cube?
Yeah, n cube, yeah. So did you know it before or did you see the screen?
No, I knew it before.
Okay, yeah. So we always do n cube computation. So as you can see in a dense matrix multiplication, we fetch order of n square data and we perform n cube operations on it. So here, for dense matrix multiplication, here dense linear algebra, it will have arithmetic intensity order of n. Okay. Now in FFT we do n log n computation. So here for FFT EI is in the range of order of log n. For I mean I don't know much about these types. Stencil I know, but right now do not explain this. These two I don't know. Now there is sparse matrix vector multiplication, and these matrix vector multiplication. Okay, so for them it is order of 1, right? That means for each, whenever you're doing matrix vector multiplication, your order of, I mean, the number of computations is also n square. So n square divided by n square is order of 1. Now, what is BLAS? So BLAS means basic linear algebra subroutine. So they have actually divided the subroutines in terms of how much computations we need to perform. So BLAS 1 means we need to perform computations order of proportional to n. In BLAS 2, we need to perform computation order of n square. And in BLAS 3, we need to perform computation order of n cube. So that all those algorithms wherever we need to do computations n proportional to n cube, we call them BLAS 3. So for BLAS 1 and BLAS 2, our AI will be constant.
This AI includes both the things. I mean, extracting the data as well as doing the computation also, because it's the ratio of two things.
Yes, yeah.
Then sir, why it is different? At some place it is order of big O of and some place it is big O of log n. Why is it so?
In FFT, you don't do the same computation, right? In FFT, you remember how many computations we do? No, n log n. That divided by n. So you can see it. Okay. That's why you get log n. And here, how it achieves order of n, that we have already shown here.
So in the back slide, previous slide, last slide. So what is the? There was a minimum of two things, and the slide before it was you were saying that we have to take the minimum of computation and data extraction, whichever is minimum, because both are going on parallel.
No. Time is opposed to performance, right? More the time, less the performance.
Yes, sir, but in this line you said that both the things are going on parallel. We will take minimum of time. So here the second term, AI, that includes both the things, computation as well as extraction of data. But and then what is the first thing?
I'll come to it. Please wait. I'll come to it. I'll explain. Till now, I'll not explain what is log.
Okay.
So this value has nothing to do with time. Log versus byte has nothing to do with time. Right here, we have for the entire application, we have defined that over the entire application, if it accesses this many bytes, we need to perform this much operations on them. Then that is the arithmetic intensity for this application.
So this is ratio, not time, basically.
Yeah, this is the ratio. Yes, this is not a time.
Yes.
This is the value of arithmetic intensity. So whenever, if your application has very high value of AI, that means you can have better data reuse. Okay, and that means you can achieve higher fraction of machine peak. So how it happens right now, it is a claim. We will give more insights, more solved examples later on. So right now we just take it as it is. I will explain it later. Okay, so one more thing you please notice that here both axis, it is logarithmic axis. Okay. So now if you have certain hardware, suppose my desktop has only 1000 adders. Okay. So in any cycle, I can only do 1000 addition operations. So my peak flops per second is only 1000. Right? That is my peak flop I can do. Okay. So now my actual performance can be even less than that. Why? Because for doing 1000, additions, I need 2000 operands. Right? I need 2000 operands, or of course, sometimes it may be possible on the same operand I can repeatedly do additions, but that's a separate idea. But I mean, whether they are same or different, that is a separate question. But I need 2000 operands, and those operands, here I'm already telling that we are fetching them from memory. Of course, there are registers, cache, so forget them. So here it is a very simple analysis. I need to fetch them from the DRAM, right? Okay, so now if DRAM has very small bandwidth, if DRAM bandwidth is very small, then they will arrive very late. Right? Although I have added, but there is no data available for doing the addition. Okay, so my actual performance will be minimum of this. Right? That means if my arithmetic intensity is here, although my machine can give me up to this much performance, I cannot achieve this performance. Why? Because the DRAM bandwidth is so low that my data is not arriving on time. So my hardware remains unutilized. But if my arithmetic intensity increases to here, suppose it reaches here, then now I'm no longer bound by the memory bandwidth. Okay, now all the hardware, all the adders I'm fully utilizing, and I have achieved the 100% peak. That means whatever is the peak performance of this processor, I'm achieving that performance. That was what I said here. If your AI is higher, then you can achieve higher fraction of machine peak. Okay, you can achieve higher fraction of the machine peak performance. So that's the idea. So maximum performance is less than this. It could be even less. So when, for example, if your arithmetic intensity is here, it doesn't mean you will actually achieve this. You can achieve, you may achieve even less, but you can't achieve more than that. Why less? There could be some more bottlenecks, right? See, here we are measuring only two bottlenecks. One is how much compute power I have and how much is my memory bandwidth. But there could be other delays. Suppose my queuing algorithm is not good, or some software issue happens, some interrupt happens. So there could be thousands of reasons which could further bring the performance down. But the point is, I can't go above this. Okay. So now, if my AI is within this range, then I call my application compute bound. If my AI is in this range, I call the application memory bound. Okay. And at this point is called a rich point, or inflection point also it's called, but I will just call it rich point. At this point, peak flop actually equals AI into memory bandwidth. That means whatever is the AI value at this point, whatever is the AI value at this point, if you multiply that with memory bandwidth, then you get the value of peak flop. Okay. So this is the minimum AI I need to achieve the peak flop. Any value higher than that, also I can achieve the peak flop, but any value lower than this, I can't achieve the peak flop. Okay, we are right on time.